Hello, physics students. This is Mrs. Altman. I know I'm not going to be in class today, so I'm just going to record myself working through the study guide. So if you take a look through this, I'm just first showing you all the equations you're going to get on the test. The angular momentum equation and the centrifugal force equation, you're not actually going to need to do anything with. I am giving you those in case they are helpful for some conceptual questions. If they are not useful to you, then don't use them. If you need any unit conversions on the test as well, they will be provided. I don't currently know which ones will or will not be on there, hence why they're not on the equation sheet, but if you need them, they will be there. Okay, let's start by working through this. I'm going to start by drawing this. So for the goal of this kind of problem, we've got a mass on one end. We are assuming that the mass of the meter stick is coming down at the 50 centimeter mark. So the torque on the left side is going to be equal to the torque on the right side. Essentially, mgr is equal to mgr, or just mr is equal to mr. So my first mass, which is the mass of the meter stick, is 0.542 kilograms. And then the second mass, which is the mass of the object, is going to be 0.322 kilograms. Now my goal is to figure out where on the meter stick it is balanced. So I know the distance between the first mass and the mass of the meter stick is 50 centimeters. So I'm going to make the distance between the end and the fulcrum, I'm going to make that x centimeters. And then I'm going to make the other one 50 minus x. And then from there, I just need to solve. I could have just as easily made the other one R2x and the other one 50 minus x. I decided to do it this way just so I wouldn't have to do 50 minus my answer when I was done. It's going to be balanced at the 31.4 centimeters mark. This is 3 sig figs. These actually won't be sig figs questions on your test, even though it's marked SF here. Okay. So how is torque similar to force? There's a bunch of things you could say. Both, there's a bunch of things that you could say here. I'm going to say that they're both vector quantities and that they both cause changes in motion. The easiest difference would be that they have different units. So torque is in Newton meters and force is just in newtons. You could also say torque is specific to rotational speed, whereas force is more general. So if you have a longer lever arm, a longer arm on a wrench, you're effectively increasing the radius. Torque is directly related to radius based off the equation that tau or torque is equal to Fr, R being the radius. So if you increase that radius, you're effectively increasing the torque, so it's easier to move things. So if you take a look at some physics textbooks, videos online, you'll see that centripetal forces are sometimes referred to as being real forces. And the reason for that is because they're the direct result of some sort of action force. So you take a bucket that's has a rope around it, you start swinging it around. The centripetal force is the direct result of you applying that force, swinging the bucket around, whereas a centrifugal force, that's the equal and opposite reaction. So there's nothing specifically causing the force. So sometimes it's called an apparent force. There's a couple other words for it. Okay, so I've got a 10-foot seesaw. It's balanced exactly in the middle. Then I've got two kids. So one sitting here and one sitting here. So if child B weighs twice as much as child A, in order to get torques balance, that child's radius has to be half of that of child A. So essentially, if child A is 2 feet from the fulcrum, child B will be 1 foot from the fulcrum. From a mathematical perspective, all we're really saying is that MGR is equal to MGR, or really MR is equal to MR. So if M is doubled, R has to be halved because we need these two values to be equal in order for this to be balanced. You could go way more into detail than this. You could talk about how the average radius is and the period have a relationship. But all I'm really looking for here is further away from the sun. You're going to have a longer year just because you're moving slower when you're further away from the sun, the energy source. So if you look back at your Newton's law of gravitational motion worksheet and you look at the problems where it's like two grapefruits or two people, you'll see that the force, it's on an order of magnitude of like 10 to the negative 10th power, as opposed to the force between a human and a planet. And that'll be around the order of magnitude of 10 to the second power. So we're seeing 10 orders of magnitudes difference. So comparatively, the forces between just two ordinary objects like two people is going to be so, so low that you just don't feel it. Weight is just force due to gravity. So if we were to somehow increase the mass of the planet, and that would lead to an increase in gravitational force, since force is directly related to mass, and therefore your weight would increase, but not your mass. So the first part is just a vocab term. This is a neap tide. That just means that the gravitational forces are in perpendicular directions. So essentially, they sort of cancel each other out a little bit. So you don't get quite as high of a high tide, and you don't get quite as low of a low tide. All right, now for the last one, we just got a calculation. And I'm just going to go up and grab the mass and radius of the Earth because I actually don't have those handy. These are not going to be sig fig questions. I put the dot there just so that it would be a little bit easier for you guys. My recommendation with questions like this is to do the addition first before you do the rest of the problem. And then these are not sig fig questions. You could have rounded this to 4 sig figs if you wanted to, and that would be completely fine, but you did not need to. All right, thank you so much for watching. Have a good night.